The down quark order quark is the second lightest of all quarks, a type of elementary particle, and a major constituent of matter. Together with the up quark, it forms the neutrons and protons of atomic nuclei. It is part of the first generation of matter, has an electric charge of -130 and a bare mass of 7004800000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 C2. Like all quarks, the down quark is an elementary fermion with spin 1/2, and experiences all four fundamental interactions: gravitation, electromagnetism, weak interactions, and strong interactions. The antiparticle of the down quark is the down antiquark, which differs from it only in that some of its properties have equal magnitude, but opposite sign. Its existence was postulated in 1964 by Murray Gell-Mann and George Zweig to explain the eightfold way classification scheme of hadrons. The down quark was first observed by experiments at the Stanford Linear Accelerator Center in 1968. History. In the beginnings of particle physics, hadrons such as protons, neutrons, and pions were thought to be elementary particles. However, as new hadrons were discovered, the particle zoo grew from a few particles in the early 1930s and 1940s to several dozens of them in the 1950s. The relationships between each of them was unclear until 1961, when Murray Gell-Mann and Yuval Ne'eman proposed a hadron classification scheme called the Eightfold Way, or in more technical terms, Souflav's symmetry. This classification scheme organized the hadrons into isospin multiplets, but the physical basis behind it was still unclear. In 1964, Gell-Mann and George Zweig proposed the quark model, then consisting only of up, down, and strange quarks. However, while the quark model explained the Eightfold Way, no direct evidence of the existence of quarks was found until 1968 at the Stanford Linear Accelerator Center. Deep inelastic scattering experiments indicated that protons had substructure, and that protons made three more fundamental particles explained the data. At first people were reluctant to identify the three bodies as quarks, instead preferring Richard Feynman's pattern description. But over time the quark theory became accepted. Mass. Despite being extremely common, the bare mass of the down quark is not well determined, but probably lies between 4.5 and 5.3700000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000more precise value. 7004790000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000h. The effective mass of quarks becomes greater because of the baryons. The effective mass of quarks becomes greater because of the binding energy caused by the gluon field between quarks. For example, the effective mass of down quarks in a proton is around 70023300000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000w 330 MeV. It cannot be straightforwardly calculated because relativistic effects have to be taken into account.